Modern AI wasn't born in some giant futuristic data center. Nope. It all started with a really simple idea. What if we could build just one artificial neuron that works kind of like our own? Well, this is the story of the Perceptron, the very first machine that learned how to see. And this is where it all began. This is the original supercomputer, the human brain. For decades, it's been the ultimate inspiration, right? A complex, beautiful mystery that has dared anyone bold enough to even try and build a thinking machine. So seriously, what would it actually take to build one? I mean, how do you even start to create a thinking machine from absolute scratch? Well, the very first pioneers did the only logical thing. They looked at the original blueprint. Which, of course, brings us to this core idea of bio-inspiration. If you're going to build a new kind of intelligence, the very first step has to be understanding our own. And to get a sense of just how massive that challenge is, look at this number, 16.34 billion. That's how many neurons are in just your cerebral cortex. Billions of tiny biological processors. Trying to replicate that? It seems completely impossible. So where did they even begin? Well, they took a classic engineering approach. Think about it. We didn't build airplanes by strapping feathers to our arms, right? No, we studied the principles of flight. And in exactly the same way, the AI pioneers didn't try to build a wet, squishy brain. They tried to figure out the fundamental principles of thought. And that meant one thing, simplifying. They had to go from the messy, tangled, beautiful reality of a biological neuron, that thing you see on the left, to a clean, simple, functional diagram on the right. This whole process is called abstraction, and it's all about boiling something down to what it really does. So what was that essential function? Well, at its core, a neuron is basically just a switch. It gathers up all these incoming signals, and if they add up and cross a certain line, a threshold, it fires off its own signal. It's either on or off, yes or no. And that super simple idea, that was the spark. And that brings us to the very first attempt to build an artificial neuron. This one wasn't based on biology, though. It was based on pure, cold logic. So let's jump back to 1943. Two researchers, McCulloch and Walter Pitts, came up with this totally revolutionary idea. They asked, what if the brain's logical process could just be described with math? Their model was just beautiful in its simplicity. Here's how it worked. An artificial neuron would get some inputs, just like a real one. Each of those inputs would have a certain weight, a level of importance. The neuron just adds them all up, checks if the total crosses a threshold, and then decides. It either fires, spitting out a 1, or it doesn't, spitting out a 0. And with this simple little model, you could actually perform basic logic. I mean, check this out. This table shows their neuron acting like a NOT gate. Give it a 0, it outputs a 1. Give it a 1, it outputs a 0. It could literally do logic, like a tiny, tiny computer. But, and this is a big but, there was a catch. The weights and the thresholds, they all had to be set by hand. So the neuron could compute, sure, but it couldn't adapt. It was more like a calculator than a student. It couldn't learn. And solving that one problem, the problem of learning, is what brings us to the real hero of our story, the very first machine that could actually learn all on its own. So let's fast forward 15 years to 1958. A psychologist named Frank Rosenblatt came along and asked what turned out to be the perfect question. He wasn't just interested in computing, he was obsessed with memory and learning. He wanted to know, how does a system get smarter over time? His answer was the perceptron. And this wasn't just another model of a neuron. No, this was a model of learning itself. Its whole purpose, as Rosenblatt put it, was to learn from experience, to perceive and recognize the world automatically. So, how did it learn? In a way that's actually incredibly human. The perceptron would look at something and make a guess. And if it got the guess wrong, it didn't just stop. It would automatically tweak its own internal wiring and then just try again. It literally learned by making mistakes. And this, right here, this is the magic ingredient. Tweaking the connections just meant changing the weights. If an input led to a wrong answer, its weight got a little nudge down. If it helped get the right answer, its weight got a nudge up. That simple feedback loop is the foundation of pretty much all modern AI. Which brings us all the way to today, because that elegant, simple idea that Rosenblatt pioneered more than 60 years ago, it's still very, very much with us. Let's take a look at its legacy.
I mean, check this out. This diagram is straight from Rosenblatt's original 1958 paper. You can see this beautiful, simple structure. A layer for sensing, a layer for thinking or association, and a layer for responding. It's so clean, so simple, and it was absolutely revolutionary.
Now, Rosenblatt didn't just come up with a cool idea. He backed it up with some serious math. He basically used probability to prove that a system like this had to learn. So let's break down the two key variables that make this whole thing tick.
To really get the math, we just need to understand two things. First is PA. That's just the probability that any single neuron will fire when it sees something. You can think of it as the network's overall energy level. But PC is where the real magic happens. It's a measure of similarity. So if you show the network a square and then a slightly different square, PC is the probability that the exact same neurons light up for both. A high PC means the network sees those two shapes as being related. And that right there is the secret to generalization.
So this is the first big equation from the paper, and it calculates PA, that probability of a neuron firing. Now, I know it looks a little intimidating, but the idea behind it is actually pretty simple. It just weighs the number of active inputs, like how many pixels are lit up on the retina, against all the possible connections that neuron has. This gave Rosenblatt a really precise way to measure and predict the network's baseline activity, even before a single bit of learning took place.
And here it is. This is the master formula. This equation calculates PG, the probability of correct generalization. This is really the heart of the entire paper. It takes those variables we just talked about, PA for the overall activity and PC for similarity, and it combines them to predict the odds that the perceptron will correctly identify an image it has never, ever seen before. Because the formula relies on the similarity of things, thanks to that PC variable, and not a perfect match, it proves the system isn't just memorizing. It is learning an abstract concept. This equation is the mathematical proof that separates simple memory from genuine intelligence. The results were just fascinating. As you can see in this learning curve straight out of the paper, that horizontal line at the bottom, NSR, that's just the number of training examples the machine has seen. The vertical line is its accuracy. And you can see it plain as day. As the perceptron gets shown more and more squares and circles, its performance just gets better and better. It is, quite literally, learning from experience.
And just how good did it get? Well, with enough of those association cells, in this particular run, 500 of them, the simulation hit over 98% accuracy. I mean, you gotta remember, for 1958, this was absolutely astounding. A machine with random wiring could be taught to see with almost perfect reliability.
But you know, this leads to a much deeper question. Is the machine just memorizing the exact squares and circles it's been shown? Or can it do something a little more human? Can it actually generalize that knowledge to recognize a square it has never, ever seen before?
This right here is the make-or-break test for real intelligence, isn't it? I mean, just memorizing things is one thing, but can it apply its learning to brand new situations? This was the next and maybe most critical phase of Rosenblatt's whole experiment.
And here is the incredible answer. In Rosenblatt's own words, he actually proved, mathematically, that after enough training, the perceptron's performance on new, totally unseen images would be just as good as its performance on the ones it trained on. It wasn't just memorizing, it was generalizing. It was learning the concept of what makes a square a square. Now, to get to this point, Rosenblatt actually tested a few different ways for the machine to learn. He called them the alpha, beta, and gamma systems. The alpha system was simple. Correct connections just keep getting stronger forever, which can get out of control. The beta system tried to fix that a bit. But the gamma system, now that was the clever one. It was a zero-sum game. For one connection to get stronger, another, an active one, had to get weaker. It created the stable, competitive system.
And this chart, which is based on another graph in his paper, makes the difference crystal clear. It's not even a contest, right? The gamma system learned way more efficiently and accurately than the others. That competitive, zero-sum approach was the secret sauce for creating a really robust and effective learning machine.
And this really draws a direct line from then to now. The perceptron had one layer. Today's deep learning networks have thousands, right? The tasks have gotten unbelievably complex. But that core principle? It's exactly the same. Learn from your mistakes by adjusting the connections. So really, the perceptron handed us the fundamental building blocks for AI. This idea of weighting inputs, the whole process of learning by adjusting those weights, the concept of a neuron only firing if a threshold is met, and this incredible idea that memory isn't in just one spot, but it's spread out across the entire network.
these concepts are still the absolute bedrock of the field.